Welcome to Lecture 30B, entitled Stokes Theorem, but in this case we're dealing with superposition problems in 3D. The material for this lecture comes from reading assignment 5, section 4.6, problem 7, which was in cylindrical geometry, and additional problems of relevance in section 6. Also, you may refer to reading assignment 0, section 5.2, and archive lecture 1C if you want to look into superposition problems at a very basic level. So the objectives of this teaching module are to apply superposition and Stokes theorem for a magnetostatics problem, and in particular the concepts and visualization skills are to determine the direction of the field and the functional dependency of the field's magnitude for each of the objects under consideration, and then secondly to illustrate the procedure for determining the total field using superposition for a three-source-free example. Well, as usual, the second slide is just a summary of the slides to follow, so we'll just skip over this and move on to the next slide. Okay, so here more or less is the description of the problem. Again, this is question 7 in chapter 4.6. So if you look at, for instance, this particular problem, there are three sources of current, two filaments. The total current in each filament is 1 ampere, and both currents are basically flowing along the z-axis direction. They're also basically not aligned with the axis of symmetry, and you also have a third current source which is in the form of a cylindrical shell which is oriented with the axis of symmetry. It has an inner radius of R1, outer radius of R2, and you're given a current density distribution but an unknown value in terms of its magnitude, that is J0, and it's pointing in the minus z hat direction. And we're given that the total field at location R200 is 0, which is more or less what we'll call our observation point. We know that the divergence of F equals 0 and curl of F equals J, which is the current flux density. And so given that information, we want to compute the total field and set that value to 0 at the observation point. So three parts to the question. First is draw an XY trace for this problem and label all relevant details. This is an important step in almost every problem that we're dealing with when we're talking about Stokes theorem's problems. The type of trace you take will very much depend on the problem, the way the problem is posed. The second part of the problem is to compute J0 as a function of R1 and R2. And thirdly, we're basically giving you the statement, suppose we solve the problem without using superposition by applying Stokes theorem directly over a circle of radius R2 on the XY plane centered on the origin. The answer we would get, which is stated there, and from which we can then compute J0, but that turns out to be an answer which is different than the result that's obtained after completing the second part of the question. So which answer is correct and why? So basically we will answer that question. So the next few slides are based on an expanded version of problem 7 in section 4.6 of reading assignment 5, but making a different choice for the direction of the differential area vector ds for one of the objects. All right, so here basically now is question 1, and it asks you to draw an XY trace for the problem and label all relevant details. And so that's essentially what I've done here. And so you have a current here at location 100, current filament. The total current flux is 1, we'll call it IB here. Here we basically have another current filament that's pointing in out of the Z direction, in the Z direction. I will call it current flux, in this case IA, and it's at location minus 100. We also have a current flux density flowing through this cylindrical shell, but it's flowing into the page. That's why we've marked this with X's. Now we also know that the direction of the field for each one of these current flux densities can be determined using a right-hand rule. So these are infinitely long filaments and shells. If the current basically is flowing out of the page, it means you put your thumb in the direction of the current and the field points in the direction in which your fingers curl. So in this case, you can sort of see the direction of the field pattern here. And then for this one, it would be this outer red that you're seeing here. And for the inner one, this one here, the current's flowing into the page. So if you apply the right-hand rule, then the field is pointing in this direction. These just represent a field line. In other words, there'll be a series of concentric rings depending on how far out you are. But this sort of more or less shows you what everything looks like, because you'll need this if you're going to do the actual calculations. We also know that the observation point here is R200 at this location, and we know at this point that the total field, due to the contribution of the fields from the shell, and these two filaments, is equal to 0. So this is more or less what you're given. And this has been summarized here on the right, here, so that you basically have a starting point. All right, so this was just telling you the directions or fields are consistent with the right-hand rule. And also just to recall that the current flux density forms closed contours since the divergence J equals 0. So this current that basically is flowing towards you from minus z hat to positive z hat, infinitely long, returns at infinity. So it basically just doubles back. Similarly, this doubles back, and similarly, this doubles back. But it's not important to sort of, sketch it. You can just sort of imagine it. Somewhere at infinity it returns. All right, so this is something that sort of a bit of an aside, because we're going to be dealing with cylindrical coordinates, because in all three examples, the two filaments are cylindrical geometry and the cylindrical shell is cylindrical geometry. But in many cases, we might actually have that the field is not in the xy plane. It might be in the yz plane, or it might be in the xz plane. We can still use cylindrical coordinates, but theta hat has a different meaning depending on the plane that you're operating in. So the ones we are typically familiar with is, in fact, the xy plane. R is defined as x squared plus y squared because it's in the xy plane, and theta hat is taken in the direction going from x to y. And this z hat is basically pointing out of the plane and is still z hat. So this is what I would call our benchmark, which is typically what we use. But let's say that in fact that the cylinder, the plane is not the xy plane, but the zy plane. In that case, the r hat vector is in the zy plane. Then the magnitude of r would be involving z squared plus y squared. And theta hat in this case, in the zy plane, would point from y to z. In this case, so the z hat vector becomes the x hat vector, because here we're dealing with the zy plane, which means x hat's pointing outwards. We could also look at the zx plane, in which case the magnitude of the radius in the zx plane would be x squared plus z squared square root. And theta hat in this case would point from z to x. The vector pointing out of the zx plane would be y hat. And so just keep this in mind. It's a very handy reference point. These are all still right-hand conventions, but applied to different planes. All right, so let's basically look at the procedure required to solve this problem. We're still basically going to be working on part 2. So we wanted to determine the field for each current flux source in an appropriate coordinate system. Well, we've established that, in fact, all three basically are cylindrical, so cylindrical symmetry applies in all three cases. Right, so that we can solve each one of these as an independent problem in cylindrical coordinates, but we're going to make sure that each of the sources' axis of symmetry is aligned with the z-axis. In the case of two filaments, they basically have to be shifted to the origin, the axes, but in the case of the cylindrical shell is already aligned with the z-axis, so there's no need to move it at all. It just stays put. Right, so that's basically the step 1. And of course, we've done problems with cylindrical symmetry already, so we'll just quickly summarize results a little bit later. The second step would be, once we've computed what the distributions look like, is to convert the field for each source into Cartesian coordinates. The reason that we need to do that is that when we sum fields, we cannot sum them in curvilinear coordinates. They have to be summed in Cartesian rectangular coordinates. All right, in order to apply the principal position. All right, so that means that everything that has been quoted in terms of cylindrical coordinates, the field direction being in either the theta hat or minus theta hat direction, has to be expressed in terms of Cartesian coordinates. And so here, the first thing I've noticed, this theta hat, which would be counterclockwise in the xy plane, this would be basically the Cartesian equivalent to theta hat. And this, of course, is the magnitude. This would be r, which is just the square root of x squared plus y squared. So if we do this for the red current filament, again, we'd be applying Stokes' theorem, and we would find that the field would take on this value, be x squared plus y squared, which is again a function of r. This would be a theta hat vector, and this would apply if x squared plus y squared is greater than or equal to 0. All right, and so this is the case for the filament. For the blue current filament, it's exactly the same. Exactly the same. So this here we're presuming that these are basically centered on the axis symmetry along the z-axis. So no difference between these two, because same basic type of object. For the cylindrical hollow shell, we have three different regions. Again, we have a discontinuous current source. We have a field, at least a current flux density, which is 0 for radius less than r1, which is the inner surface of the shell. Then we have a current distribution inside the shell, and we have a current distribution outside the shell. So we have the three cases to consider. Inside the shell, there's no field. That's interior to the shell. Inside the shell, then we have this form. But notice that here, the sign has been reversed. So this minus y is now a positive y, and this positive x becomes a minus x. Why? Because the field is in a clockwise direction. Okay, go back to the previous slide where we looked at the xy trace, and you could see that the field was in the clockwise direction. So this is a proper representation of the field. If you're outside, again, it's still counterclockwise. Then it takes on this form, and this is for x squared plus y squared greater than r2 squared. So we expect this scalar function to differ from this scalar function when looking at the field inside the shell versus the field exterior to the shell. All right, so now we have to look at the specific problem. This, by the way, is just an arbitrary observation point. In our case, the observation point lies right about there. But nevertheless, it's easier to visualize here. So here, for instance, are the coordinates of the filament. The coordinates of the filament. So this would be effectively relative to an axis of symmetry. If everything were to move over here, then this distance is preserved. And this basic distance basically would be preserved. This is already oriented with the axis of symmetry, and so this basically is with respect to the cylindrical shell. So there are three different paths that we're looking at depending on which one of the objects we're concerned about. So the coordinates of an observation point with respect to the local reference point, the local reference point being this or this or this, is just the difference between the positions of the two. So for instance, the coordinates of the observation point will be x1, y1, z1, which is shown here. And the coordinates basically of the local reference point, so you have three possible reference points, are just x0, y0, z0. So the difference between those two basically would give you the relative position with respect to a given reference point. And so for instance, x0, y0, z0 for the blue filament is 1, 0, 0, 0, 0 for the cylindrical shell, and for the red filament it would be minus 1, 0, 0. Observation point, which is whatever it is, so you subtract this 2, and this would be the information which is useful once we're trying to determine what to substitute. All right, so the next step would be to rewrite the field for the two filaments and the field for the shell with respect to the observation point, which is sort of what we were alluding to in the previous slide. So the locations of the axis symmetry on an x-right trace for FAL and FAR are minus 1, 0, 0 and 1, 0, 0 respectively, and are different from the origin. Hence, we cannot just simply add Cartesian coordinate expressions for AFL and FR when trying to compute the total field at some arbitrary location, which we were going to refer to as the observation point. So here again, it's just summarizing what was on the previous slide. Consider the location of the axis of symmetry on an XY trace for a specific vector field is some point x0, y0, z0, which we call our local reference point. Now consider an observation point x1, y, z1, where we want to find the total field. In our case, that would be along the x-axis at position R2, 0, 0, 0. The coordinates of the observation point with respect to the local reference point would be given by just the difference between the x, y's, and z components of the reference point, of the observation point and the reference point. So let's go through each one of the three current flux density sources individually, one by one. So for filament AL, the local reference point had these coordinates. The observation point, which is a known, which is given, has this one. So the coordinates of the observation point with respect to the local reference point is just subtracting x, y's, and z coordinates of these two, and we end up with this solution. So that means that if we go back to our previous expressions we had derived for FAL at the observation point, the x's and y's and z's get replaced by x1 minus x0, y1 minus y0. In this case, there is no z1 minus z0, so it's not necessary to make use of it. And so we end up with this now as being the modified expression. And so we can basically substitute in everything. We know what x1 minus x0 is. We've done all of those calculations here. And so we end up with a simplified expression for FAL that looks like this. This is yet to be determined, but we know that we need to evaluate R2 plus 1. We do the same thing for filament AR. There's the local reference point. Here's the observation point, and this is the difference between the two. Similarly, the only difference now between FAL and FAR is the x1 minus x0 and y minus y0 values for this case are different. And so if you make the substitutions from here, there's the x1 minus x0 component, and y minus y0 and z1 minus z0 components are both 0. And we end up with this expression here. Note that R2 is greater than 1. R2 is greater than 1. Therefore, x1 minus x0 is greater than 0. All right, so that basically can be this, from the, that can be determined from the initial XY trace, the problem statement. All right, for the cylindrical shell B, this is our local reference point. The observation point is still the same, and so the coordinates of the observation point with respect to the local reference point will take on this value. Hence, the correct expression for FB with respect to the observation point in this case will just be this value, which is when you're just outside the cylinder. And of course, our observation point is outside the cylinder, so this is in fact the correct expression to use. All right, having done that, then we can compute the total field. It would be just the sum of the three contributions, which is shown here, and we can basically just add them together and simplify it to something that looks like that. All right, so next thing basically is to compute J0 as a function of R1 and R2. So we're going to use Stokes' theorem to compute FA for both filamentary wires and FB for the cylindrical shell. And so here we've shown what Stokes' theorem is for the filamentary wires. This would be AL and AR. And then for the cylindrical shell, basically same thing, but just different labels. So we'll do FAL and FAR first. We want to compute what this is. This is the scalar function that precedes the vector expression, the unit vectors. Okay, we're going to use Stokes' theorem. So the left-hand side of Stokes' theorem, I guess we said it never changes. In case of cylindrical coordinates, you're always going to have something that looks like this. On the right-hand side, we have this. Now, this is a filament. So recall with the filament that the JL would be I divided by pi r delta r. And it's in the z direction, so that's 0, 0, 1. And NSDS, basically the surface area vector, is in the z-hat direction. We've chosen that to be the case. That's 0, 0, 1. So this is the differential surface area vector, time RD, RD, theta, 0, 0, 1. All right, if we integrate this, recall basically that when you're integrating delta r down here, 2 pi 0, 0, r just greater than 0, this is equal to 1. All right, so when we do this calculation, this is going to be equal to 1. And again, the total current flux, which this represents, was stated being equal to 1. So we know that this has to be equal to 1. So this is the right-hand side. So now you equate the left-hand side with the right-hand side, and you end up with this expression. Again, this has to be in Cartesian, so this r gets replaced by x squared plus y squared. Similarly, you can do it for the filament on the right side, exactly the same expression, no difference. If you take a look at it, you end up with the same expression. All right, so now we do the computation of field in cylindrical coordinates for the shell. So this is the scalar function. So we end up here with 2 pi r h of r. And on the right-hand side, basically, we have the current flux. But in this case, the only contribution to the current flux is from R1 to R2. And the current's in the negative z direction. That's why you see -1 here. And we've chosen the area vector to be in the same direction as well. Okay, so this is -1 to be consistent with the right-hand rule. And so when you integrate, you end up with pi j naught r2 squared minus r1 squared. All right, so this is what we get. And this would be the value that you would get if you're being exterior to the shell, this h of r. And we've chosen to do that anyways because we are just at the outside periphery of the shell at R2, and so this is a perfectly valid expression. Okay, so we equate this with this, and doing the computation, this will involve r, but r can be replaced by square root x plus y squared. So now this is the value for h square root x squared plus y squared. All right, so now we just put all the pieces together. So again, we have to basically do the computation with respect to the observation point. So this becomes x1 minus x naught. This becomes y1 minus y naught, which is f of r2 plus r1. Same thing for AR. And for the case of the cylindrical shell, it was just hr2. So now we go back to the expressions that we had on the previous page. Substituting fr2 plus 1, we end up with this expression. And for the filament AR, this was evaluated R2 minus 1. We end up with this expression. And HR2 basically is still the same. This is 1 here. So now that we have actual physical values for these, we're basically total field. This has to be equal to 0. And so putting value in for this, value in for this, and the value in for this, you have a 0 x component, 0 z component. But all of this basically is the y component. It has to be totaling to 0. So the sum of these must be equal to 0. All right, if that's the case, you can solve for J naught. And this is the final result that you get after solving for J naught. All right, so the last part of the problem is 3. Suppose we solve the problem without using superposition by applying Stokes' theorem directly over the circle radius R2 on the xy plane center on the origin. The answer we would get is 0 times 2 pi R2 is equal to 2 minus j naught pi r2 squared minus r1 squared. All right, so you might say, well, this is the left-hand side. The field is going to be 0 because we've stated that it's going to be 0 at this point here. This is a contribution, say, to this filament. And there's a contribution to the filament here. Both are positive contribution, whereas the current flux in this one is in the opposite direction, so you end a minus sign here. So this would be the current flux due to this cylindrical, ring that you see here. Right, if you then solve for J naught, you end up with this result, but that's different from part 2, which answer is correct and why. All right, so this is more or less the explanation. The field due to all 3 current flux densities taken together is not symmetric, unlike FAL, FAR, and FB taken as isolated current flux densities. However, the statement integral f dot dl equals 2 pi r2f is only correct if the field is in the same direction of the contour, which is not true, because the field basically that we're looking here, if we draw a contour, will not basically be pointing always the same direction, because each one of these, this current flux density distribution, this current flux, will all contribute to a field here. And those values will basically be changing as you move along the contour. And so they can't be possibly pointing in the same direction. Also, the magnitude is not uniform. Remember that when we did the computation, we assumed F was uniform. That's not going to be the case as well. Okay? So that's why using superposition to break up a problem into smaller symmetric problems is the correct way. Here, basically, there is no symmetry, and therefore this relationship has absolutely no meaning. Well, that basically concludes Lecture 30B. Thank you for listening.